What's up, y'all? Welcome to section 8.5, using exponential and logarithmic functions in word problems. You made it to the end of the chapter. Let's actually put the pedal to the metal and see what this looks like in actual reality. So we've got a whole bunch of word problems and applications. Here's our first one. Population. In 2016, the population of Florida was 20.61 million people. And then in 2000, way earlier, 16 years earlier, it was 15.98 million. So you're assuming there's continuous, keyword, continuous exponential growth, predict when the population will reach 25 million people. Continuous growth means you use that APERT formula right here. You can write it down. So you have to predict when will it reach 25. It was 15. Then it was 20. And when's it going to be 25? So let's just do that part first. Let's do part A. So just organizing ourselves here, we've got anytime we have lots and lots of numbers, maybe it's just a lot easier to figure out to put it on a table. So this is your knowns and unknowns table. Years, we've got 2000, 2016, and then an unknown year as well. We've got years since 20. T is going to not be, we're not going to use the number 2000, the number 2016. Sometimes it just gets a little too unwieldy. So it's a lot easier to type things in and to think about if we just use years since the beginning of this experiment, which started back in the year 2000. So years since 2000, this is 0, this is 16, and then we'll have another number over here. Population in millions, and I'm not going to type in 15,980,000, 000. No, let's just use the population and we'll know that it's in millions. So it's a 15.98 million, 20.61 million, and 25 million. Using APERT, what we're going to do is, and the thing that we don't know is this rate here. We don't know what the Florida growth rate is, assuming that it's constant, continuous exponential growth. So let's use these first four numbers, the top four numbers, to figure out what R is in the first place. And so we're going to set up the two different versions of this equation. Once with R, once without R to find R. And then once we know what R is, we'll use it a second time to figure out a new time. So APERT, we got 20.61 is equal to 15.98. Dividing both sides, undoing the multiplication here, we got 20.61 divided by 15.98. And in order to be more exact, I'm not gonna type in the division in here and get an answer and hit enter. No, I'm going to hit enter only at the very end. I'm going to move things around in this equation so that I eventually get what we need, and I can hit enter once and only round once, and I'll be way more exact in that way. So here we've got a giant number equals e to an exponent. So I'm going to change that, convert it from exponential form to a logarithmic form. This is base e, so it'll be turned into the natural log of, and then all of this over here is equal to the exponent, which is all by itself, r times 16. Dividing both sides by 16, we get r. The rate is going to be equal to all of this, which I can type into a calculator. It looks like this. Control, I think I'm going to start off with a fraction first. Control, divide in the numerator. Control, e gives me the natural log, and then I got 20.61, and then divided by 15.98. Exit the natural log, go down to the denominator and put a 16, and then you hit enter, and you get what you need. 0.0159 approximately, rounded to the nearest thousandth of a rate. Okay, so now that we know what the R is, we can use it to make a prediction. And so this is still part A. We're going to find now this unknown population, this unknown year. Well, we do know that eventually we want to get up to 25 million, and we're starting at 15.98 million. With this, now that we know the rate, we can put it in here and solve for t. Dividing by both sides by 15.98 to undo the multiplication. And then here we're going to have a natural log again. And then dividing both sides to undo this multiplication again. I'm not going to type it in. It's going to be very similar. But this is what it looks like. T is equal to about 28 years, if you want to round, or in the year 2028. That's part A. Part B looks like this. California's population in 2000 was 33.9 million, and its population growth can be modeled by this equation. Graphically determine when Florida's population will surpass California's. Okay, so you can see that I've switched over to Desmos. I've typed this in. You don't have to do this right now. If you need to, you can later. But I just want to show you that we got this red state, Florida, right here, and this blue state, California, and so I've typed in the Florida's initial population was 15.98 in the year 2000. It's got the growth rate that we calculated, and then Florida has got, the blue state, California, has got a higher initial population in the year 2000, but it's not quite growing as quickly. So we've got this slow growth that's going to eventually be caught up by the fast growth, and at some point they're going to catch each other. And so this intersection point is at 112.25. That means in 112 years from the year 2000 is when they're going to equal each other, and eventually Florida is going to surpass. According to this growth model, Florida will have more people than California. That's what we're looking at here, and that's what the growth model predicts. So that's part B. Science. The half-life of a radioactive substance is the time it takes for half of all the atoms in the substance to disintegrate. The radioactive substance thorium-230 is used to determine the ages of cave formations and coral. The half-life of 230 is 15,381 years. So that means that this element here, this unstable element, will decay at a very slow rate, and it'll take 15,000 years for it to turn into something else, or for half of it to turn into something else. And how much of a 2-gram sample of thorium-238 should be left after 15,000 years? 1,500 years. So let's use a PERT. Let's organize our knowns and unknowns. Years 0. At year 0, we've got 2 grams. At year 15,381, we've got 1 gram, which is half of 2. And we want to know how much you've got left in the year 15,000. Or after 1,500 years. We're going to use a PERT. 1 equals 2 times e to the r. We don't know what the r is. It's not given here, so that's an unknown. We have to calculate it first, and then we'll use the r value to calculate the final amount. So here, if we start with 2 and we go down to 1, if we divide both sides by 2, we get 0.5. Anytime you have a half-life, you could start with this formula here. 0.5 is equal to 50%. Half of what you're looking at is equal to e raised to the r 15,381. Even if you weren't given with the idea of you have 2 and then go down to 1, you could start with just it's at 50% half-life. 1/2 or 50% is equal to e raised to the RT. The time is 15,381, and so we're going to reorganize everything from an exponential into a logarithmic. The base is e. We're taking the power is 0.5, and the exponent is all by itself, r times 15,381. Dividing both sides by 15,381, we get this. It's a negative rate, which means it's decaying. It's getting smaller. Anytime you have an exponential decay, the exponent, the r value, has got to be negative in order to make it slope downward that way. And so that's what we have here. Continuous exponential rate, r. If you want it to grow, the r has got to be greater than 0 and be positive. If you want it to decay, the rate has got to be less than 0 and be negative. Now that we have the rate, we can plug it into a PERT. We get a, the final amount, a is equal to 2, the initial amount, times e raised to the rate that we have here. It's an incredibly small rate because this thing, it takes 15,000 years to decay. But in any case, that's the nature of what's going on. And you multiply it by 1,500, which is with the years. The only thing we don't know is the grams. You can type all this into a calculator, you get 1.87 grams. After only 1,500 years, you still have pretty close to 2 grams. But if you can measure it here, if you measure down to the nearest hundredth of a gram, then you can calculate 1,500 years. That's how old a cave drawing should be. Or if 1,500 years ago someone built a fire, and there's like coal in a cave or chalk, you can calculate how old it is, or how old it was when it was formed. Archaeology, same idea. Carbon-14 is used to date objects in a method called radioactive carbon dating. Carbon-14 has a half-life of 5,730 years and a decay constant. Oh, they give it to us. The R, they didn't give it to us here, but now R is 0.00012. In 2016, charcoal flakes from the excavation sites of an ancient human settlement in Canada, this is a real story, were sent for radioactive carbon dating. The charcoal flakes were found to contain about 13.6% of the carbon-14 as found in living things. So here, we knew that it was going to go, we knew there were 2 grams and it was going down to 1 gram, and this is how long it took. But we don't know how, we know that the constant R is this, and notice I'm making it negative. In here, it was just the constant here, but we have to make it negative in order to make sure that the equation represents decay. And we know that we have 13.6% of the original. What we don't know is the time. So there's actually, so in thinking about it, you're like, well, how many grams of charcoal flakes are we looking at here? Are we looking at 100 grams? Did it start off with 100 grams of carbon-14 and then go down to 13.6 grams? Or do we start off with 1,000 grams and go down to 136? Or do we start off with 1 gram and go down to 0.136 grams? All 3 of these cases could be possible based on the fact that you have a 13.6% carbon-14 left. And actually, it doesn't matter which one of these we choose, because when we isolate it, when we divide both sides and undo this multiplication, we get 0.136. That's the 13.6% written as a decimal. So in point of fact, if you wanted to, it might be a lot easier to think about it as A divided by P is this 13.6. Moving this P over to the other side, we don't know what A is, we don't know what P is individually, but we do know that A divided by P is 0.136. So just a good start right here. 0.136 is equal to E raised to the negative 0.00012t. Now we change this to a natural log, and you can see here the natural log of 0.136 is equal to negative 0.00012t. And then I'll show you what this looks like to type into your Inspire. You got, I'm going to do the division symbol, a big giant fraction there first, and a natural log of 0.136, and the numerator, and then negative button 0.000, and then I want you to figure out what I should type next. What do I put here? And then when I hit enter, I should get about 16,626 years. That's some super old human settlements in Canada. 16,000 years. That's prehistory. So there's a formula here we can use. When you have a percent remaining, you can just reorganize this formula into A divided by P is equal to ERT when you're given a percent remaining equation. That's all I got, y'all. That's everything I need to teach you from Chapter 8. So go forth and exponentially multiply. I don't know what I mean by that. But I do want to say, actually, that my favorite Saturday Night Live cast member is Kenan Thompson. He's so funny. Love that guy. He's been funny for years. Always will be. Always has been, and Kenan Thompson is the guy. I want you to tell me, if you watch Saturday Night Live, what's your favorite cast member. Take care, and I'll see you in class.